では次は、リガード府のミンチュさんです。お願いいたします。
Good morning, good afternoon, everyone. I'm Mingxu, a Doctor II student in Yamauchi Library Department of Chemistry. Now I will share my presentation. My research topic is electricity-driven carbon dioxide selectivity conversion. So while I focus on the research of the electricity-driven carbon dioxide conversion, actually it has a big background. From the left figure, we can see for the past thousands of years, the carbon dioxide concentration is kept well lower than 300 ppm. But in the recently, the carbon dioxide concentration is constantly increasing. Now the concentration for the carbon dioxide already larger than 400 ppm. That leads the problem is that the world temperature is increasing. From the red figure, we can see for the past 50 years, the average world temperature already increasing around 1 degree Celsius. So we need find out to solve this problem. So recently the renewable electricity give our tons. From the left figure, we can see for the past 10 years, the renewable electricity capacitance is increasing. That lead to the result is that the renewable electricity cost is decreased. From the red figure, we can see now the renewable electricity cost already lower than the fossil fuel electricity cost. If such cheap electricity can be used to driven carbon dioxide conversion, that will be very meaningful. Like this game, we can use the renewable electricity driven the carbon dioxide conversion to the useful chemicals and fuels to support our life. So in my research, considering the energy density for different carbon reduction products, so I focus on the multi-carbon products using the electrochemical carbon dioxide conversion. So next is how can we produce the multi-carbon products from the carbon dioxide? And the mental catalyst can help us. From this figure, we can see among various mental catalysts, only the copper can convert carbon dioxide to multi-carbon products. But we can also see the carbon reduction products are widely distributed. It's not only including the multi-carbon products, but also including a large amount of the monocarbon products. That means the selectivity is low. So we have to find out method increasing the selectivity. Recently, the oxidized derived copper has been investigated as a candidate to enhance the multi-carbon product selectivity. And several researchers offer the different mechanisms. For example, the residual oxygen atoms. In this work, they introduced the residual oxygen maybe can interact with the carbon dioxide to enhance the selectivity for the ethylene. And some researchers believe the surface hydroxyl can bond into the surface of the copper and interact with some carbon monoxide species and produce the carbon 2+ products. And another researcher believe that because the different oxidation state for the copper, so we can produce the different products. For example, the ethylene, methane, or some hydrogen. And recently, some researchers recommend, because during the reduction reaction, all of the copper oxide or copper oxide will be reduced by apply the negative potential. So they believe the main reason is the grain size. The grain size becomes smaller, maybe influence the selectivity for the multi-carbon products. So no matter what mechanisms, we synthesize two kinds of oxide-derived copper catalyst for the carbon dioxide reduction reaction. The above figure describes the synthesize procedure, and from the same image, we can see the morphology is needle-like nanowells modified on the carbon 4. And the morphology for the two kinds of catalysis is nearly same. And then we use the two kinds of catalysis to do the carbon dioxide reduction reaction to check the performance. From this slide, we can see the two kinds of carbon catalyst carbon dioxide performance. The copper hydroxide catalyst show the Friday efficiency for the multi-carbon products is around 62%, and the copper oxide selectivity catalyst show as high as the Friday efficiency around 80%. So we can get the conclusion that the copper oxide show the higher selectivity than the copper hydroxide. So in order to find out the reason, I checked the oxidation state using the XPS. From the left figure, we can see for the before the carbon dioxide reduction, we can easily distinguish the different state of the copper hydroxide or copper oxide peak. But for after the carbon dioxide reduction, we can find that the peak related to the copper will be shifted to the low binding energy. That means the copper hydroxide or copper oxide will be reduced during the reaction with different degree. So I recommend, if we want to know exactly the oxidation state, we should use some in situ experiment to check the possible reason. Finally, summarize. One, I synthesize the oxide-derived copper catalyst for the high selective carbon dioxide reduction to the multi-carbon chemicals. And the second is characterize the oxidation state of each catalyst before and after carbon dioxide reduction reaction. And the final is outline the physical in situ measurement is necessary to discuss the catalyst state during the carbon dioxide reduction reaction. Thanks for your attention.
はい、それではただいまの、ご講演に関しまして、報告ですね、関しましてご質問があれば、別室機能を使いお知らせください。産業界の皆様いかがでしょうか。はい、この機会ですので、よろしければ挙手機能をお使いください。ちょっと上がってこないようですので、そうですね、これはCO2 削減、 排出を、削減するという方向ではなく、CO2 をうまく利用してっていう、次のものに変えていくという、研究になりまして、これからもご覧いただければと思います。ありがとうございました。